Warm greetings. The South African Mathematics Foundation, whose website address is www.samf.ac.za, hosts a number of mathematics competitions directed at high school students at the junior and the senior level. The juniors referring to the learners who are up to grade 9, the seniors from grade 10 onwards. Today we are going to unpack one of the competitions that was administered in the year 2021, and this is part of a long series of presentations, Zoom presentations, which tries to unpack the many competitions that the South African Maths Foundation administers. This particular one was set for the round 3, the final round of the Junior Olympiad, South African Mathematics Olympiad, in the year 2021. So with those few words, let's get on with the work at hand. Okay. Okay, so as you can see, we are doing this 2021 SAMO round 3 paper. The first question asks the following: which number is larger? 2 times the square root of 21, or 20 times the square root of 21. Okay, you've got square roots here. So as it stands, you don't know what the square root of 2021 is, but you do know it's square. So why not square both of them and see which is larger? So when you do that, you'll see that 2 root 2021 squared is 4. 2 times 2 is 4. And the square root of 2021 multiplied by itself is 2021. And that is 8084. I'll try the other one. 20 root 21, square that one. So 20 squared is 400. And the square root of 21 squared is just 21. So that gives you 8,400. So now you can see which is larger. Answer is the second one. If the squares are larger, then obviously the number itself has to be larger. Okay, so let's get on to the next question. I usually have the solutions written in advance, and I normally briefly display them like this, and you can see it's a way to check to see what the answer is, whether I've got the correct answer. Okay, let's get on to the second problem. The second problem states the following: to convert Fahrenheit and Celsius temperature scales, we use the following formula. In South Africa, we use the centigrade formula, but before that, we used to use the Fahrenheit. I think Fahrenheit is still in vogue in countries like the United States, I think, and maybe Britain. And there, the Fahrenheit scale is a little bit weird. The freezing point is 32 degrees and the boiling point is 212 degrees. Right? But centigrade is very much more natural. Freezing is 0 and the boiling point is 100 degrees. So there is a conversion between these two. Like for instance, in this case here, as I said, if C is equal, this is a formula for the conversion. Let's take if C equals 0, F is equal to 32. I just said that. These, both of them represent the same temperature, which is the freezing point. And if C is equal to 100, right, then F is equal to 9 over 5 times 100 plus 32, and that is 212. I mentioned this. We normally write down 212 degrees Fahrenheit, and that is equal to the 100 degrees centigrade. Okay, now the actual question is at which temperature do the two temperature scales give the same reading? Okay, so in other words, you want the F value to be the same value. Right? So therefore, we've got the formula for F. So we'll replace F by C. In that formula, you got one equation with one unknown. We can solve. I don't like fractions, so I can multiply by 5 right throughout. And the 5 is cancelled to get this. And therefore, you get that 5C minus 9C is equal to 160. And that gives you minus 4C is 160 degrees. So it's minus 40 degrees. Now that's a very cold temperature. Okay, so at minus 40 degrees, both these different scales will read the same. Okay, it'll be the same number. So that's the answer to that question. Let's just check to see. Yeah, there it is. We got the same answer. Okay. Let's get on to question 3. Question 3 is kind of a long story here. Basically, I'm just going to unpack this. I'm not going to read this thing as it is. The first part tells you that you got an equilateral triangle. So all the sides are equal. And and what happens is you've got a point inside the triangle. And from this point, perpendiculars are drawn. To the other sides. You drop a perpendicular. You drop a perpendicular here. These are 90 degrees. To give you the length of the side, it's 6 root 3. Okay, so all the sides are 6 root 3. And they also tell you that so this is D, and this is E, and this is F, and this is the point P. And we are told that PD is equal to 1. So this perpendicular here is equal to 1, and PE is equal to 3. That perpendicular. Okay, sorry, I'm squeezing this thing in. But I just want to get a feel of what this is all about. Now, they say that when you add these three perpendiculars, you'll always get the same answer. That's a very interesting fact about equilateral triangles. Okay, I'm going to just go down to the next page. I've set aside a page to do my calculations here. Okay, so this is what you've got. And the interesting thing about this, as I was saying, is that the sum of these three perpendiculars, no matter where you take it, if I took a point here, and if you draw three perpendiculars, and if you add those three, you'll always get the same answer, which is quite remarkable. The sum of these three perpendiculars will always give you the same answer. All right. So that is what we will set out to prove just now. But the first question was, what is the area, or the areas of these triangles? You are asked to find the areas of this triangle. From P, AB, the small triangle here. The height is given. And in the other one is this one. What is the area of that triangle? Well, this is straightforward because the area of a triangle is half base times height. And you have, in this case, you choose the base to be AB and the height to be, it's given as 1. So the area of APB it's a black triangle, is equal to half base. It's given that the sides are, all the sides are 6 root 3. So it's an equilateral triangle, and the height is given as 1. So that simplifies to 3 root 3. So it's a straightforward problem. The other one also, the other one is area of APB. Oh, I'm sorry, it's actually APC, the red triangle. And the area of that is same base, APC, because it's an equilateral triangle, but the height here is 3. So that gives you 9 root 3. Okay. And then they ask us to prove that the sum of the three perpendiculars is equal to the height of the triangle. I told you they all are equal, the sum of the three. They're actually equal to the height of the large triangle. All right, so what we're going to prove here in this, that the three heights are PD. Let's put that required to prove. The three heights are PD, PE, and PF. and you asked to prove that this is equal to H. Right. So in other words, it doesn't matter where P is. The sum here is always equal to this, the height of the triangle. Okay, now to prove this, you calculate the sum of the three areas. You know, we wrote down those three areas there, the two areas. Whenever you got a point inside a triangle, it spans out three areas. If you join that point to the three vertices, you'll get three triangles. And I'm going to say, I'm going to use the fact that the sum of the areas of these three triangles is equal to the area of the large triangle. And I'm going to work it from P. This is the point that we're talking about. So we're going to work out the sum of the three areas. I'm going to abuse notation. I'll put PAB. This means the area of triangle PAB plus triangle PBC plus triangle PCA is equal to triangle ABC. This is a picture I had just now. That the sum of the three triangles, their areas, is equal to the area of the whole triangle. Okay, now let's just take these, each one. Triangle PAB is a half AB. I'm just going to call it PD. I'm not going to give it the value that was given in the problem. Half AB times PD, and PBC is half BC times PF. That's this triangle here. And that's PBC, triangle PBC. It's half base, which is BC, times PF. That's what I got here. Right? And just like that, you have the third triangle is half CA that one there times the height there, which is PE. But the AB, BC, and CA are all equal because this is an equilateral triangle. So I can just take out half AB into the other factor is PD plus PF plus PE. Right? Because all these are equal. This is equal to AB, and this is also equal to AB. So I can take out half AB as one factor. Right? But now this is the area of triangle ABC. Right? I'm looking at that figure, that one there. And the area of triangle ABC is half. Let's make this BC. Sorry, instead of AB, I'm going to write down BC. You'll see just now why. Doesn't matter whether you're putting AB or BC or CA, they're all equal. But this is equal to the area of this triangle here, the entire triangle. and that's half base. The base is BC times the height, which is H. Now you can see I can cancel the halves. I can cancel the BCs, and I will have the PD plus PE plus PF is H. That's exactly what I wanted. That the sum of these three distances is equal to the height of the triangle. Okay. So that actually allows us to calculate. You see, we've got two of these heights. We got this one. Yeah, it's there. This is 1 and this is 3. And we don't know this, let's call it X. So let P F equal to X. And the next question is, calculate PF. Okay, now from what we have just proved, we proved that the sum of the three heights is 1 plus 3 plus PF. That's the third height. Right? The sum of the three is 1 plus 3. Those two were given, plus the third height is equal to the height of the triangle. Right? Now, the height of the triangle, you can use Pythagoras to calculate it. That AC was given as 6 root 3. Now, this is an isosceles triangle. And whenever you got an isosceles triangle and you drop a perpendicular from the vertex, it bisects the third side. This is a very, very popular fact. An isosceles triangle, then if you drop a perpendicular, these are equal, these are 90 degrees, and those angles are also equal there. So you have those two triangles that split into identical triangles. So in particular, this part here, the whole thing is 6 root 3. So this part is 3 root 3. Right? Because this perpendicular is also the median. Now we have got two sides of a right angle triangle. Right? Just to point out what the right angle triangle is. That one. That's where the H is. And you have that. So if you focus our attention on that right angle triangle, you have the H is equal to the square root of this squared, the hypotenuse squared, which is 36 times 3. When you square, this 6 times 6 is 36. Square root of 3 squared is 3. Now you have to put minus here, because the sum of these two is equal to 6 root 3 squared. So minus this squared. When you square this one here, you have minus 3 times 3 is 9 times 3. So the square root of 3 squared is 3. So here you can take out 3 is a common factor. So you can square root of 3 times 36 minus 9 is 27. Okay, so this one here, you can get the answer straight away. You can either say 3 times 27 is 81. The answer is 9. Or I prefer taking one of these threes here and put it into that 3 times 3, and I've taken a divide this by 3 and multiply by 3. So I multiply that by 3 and divide by 3, and that's what you get, that the area is 9. So this is the answer to the problem. Oh, not yet. I need to calculate PF. So I have 4 plus PF is 9. So therefore PF is equal to 5. Okay, on the left-hand side, I've got 4 plus PF. On the right-hand side, I've got 9. Okay, so that takes care of that problem. Let's get on to the next. Uh, let's see what solution I had. I don't know whether there was any other question. We can check. So there it is. We proved the second part, PD plus PE plus PF equals H. And the last part is calculate the length of PF. And we saw that it was 5. We also calculate the areas of triangles APB and BPC. So we've done everything. I didn't want to read this long essay. I'll explain to you what it's all about. Let's now get on to, okay, so this was the solution. Oh, we're still a long way. Okay, so we're doing problem number 4 now. Problem number 4. Steve adds consecutive odd numbers, 1 plus 3 plus 5 plus 7, up to a certain point, and claims that the total sum is 2020. Okay, let's just analyze this thing here. When you're adding consecutive odd numbers, a very interesting thing happens. Let me just get back to my black. So 1 is equal to 1. Okay, 1 plus 3 is 4, which is 2 squared. 1 plus 3 plus 5, 4 plus 5 is 9, that's 3 squared. 1 plus 3 plus 5 plus 7 is 9 plus 7, which is 16, it's 4 squared. So there's a very beautiful formula. If you add the first 4 odd numbers, you get 4 squared. The first 3 odd numbers, you get 3 squared. So in general, 1 plus 3 plus 5 plus 7, going up to n terms. In other words, the sum of the first n odd numbers is n squared. Okay, so that's an important fact. It's nice for you to remember it, because obviously here they are assuming that you know this formula, right? Okay, go and research it and find out what's the reason for this. Try to prove that this is always true. I'm not going to do that now. Now, they say that this is actually equal to 2020. It was calculated, but 2020 is not a square. So therefore, Steve made a mistake, because 2020 is not a square. Not a square now. not a square number, right? Now they say, could it be that Steve accidentally skipped a number? If so, which one? Now, the sum here is given to be 2020, right? I think by now you know that 2025 was a perfect square, right? So his 2025 was a perfect square. So it means that you had to add 5 to this to make it a perfect square. So he left out 5, you see. Could it be that Steve accidentally skipped a number? If so, which one? Right? It has to be 5. Right? Because you've got that Steve sum. So then you'll have that 1 plus 3 plus 7, missed out 5. That will be equal to 2025 minus 5. Because if you're stuck in the 5 days, 2025, I've removed it, that gives you 2020. So that tells you that the missing number is 5. Okay, so that's the first part. And it is true that Steve skipped a number and the number is 5. The part C is saying, show that Steve didn't accidentally add the same number twice. Now, the error, you know it's definitely an error, but exactly what was the error? We said, look, maybe he skipped a number, and that was possible because we saw that if you skipped 5, you'll get to that answer. But now the question is, what was the error that he made? Why did he get the wrong answer? Maybe he repeated some number. And this question says, look, did he repeat a number? And the question says, show that he didn't accidentally repeat a number. So if you want to show that he didn't add the same number twice, right, we prove by contradiction. Right? So suppose he added the same number twice. Twice to get the wrong answer, 2020. All right, now I'm going to write down exactly what we are saying here. So it's 1 plus 3 plus 5, and so on. Then he comes to A. Let's call this A. And then at some point, where there was a B, now this is the correct one. This is 2025. But this guy, he did this. And in place of B, he put A. He replaced it by something else. So that is 2020. That's how you got the wrong answer. Right. Now they're asking, is it possible that he has got the same number twice? Okay, and we are saying, suppose it is, now we can subtract these two. All these cancel, even the A's cancel. But here, you got B minus A. And all the others are the same, so they all become 0. And that is the same as 2025 minus 2020. which is 5. So your B minus A is 5. But B and A are both odd numbers. B and A or A and B are both odd. Now, if you subtract two odd numbers, like what you got here, you'll always get an even number. Think about it. Right? Take any two odd numbers, if you subtract them, you'll get an even number. Right? And the reason for that is that if you remove 1 from here, 58, and you add 1 to this, oh, yeah, actually this is the same as 58 minus 26. Because you take out the 1 from there, take out 1 minus 1 is 0. Now you got the difference of two even numbers. That's quite clear. That's always even. So the difference between two odd numbers is even. And we've got that this difference between these two odd numbers is 5. So B minus A is an even number. And that is equal to 5. And this is clearly impossible. Right? Or rather than impossible, it's a contradiction. So if you make this assumption that he added the same number twice, then you come to an impossible situation. So therefore, he did not. Suppose he added the same number twice. And we get a contradiction. So therefore, he didn't. Therefore, yeah, proved. I'm going to write this thing out now. Here is, we're saying, suppose Steve didn't actually add the same number twice. So the opposite of that is he did accidentally. Yeah, I'm sorry. We said if he did add the same number twice, it's impossible because you come to an impossible situation where an odd number is equal to an even number. But, so therefore, he didn't accidentally add the same number twice. If he did, it's a contradiction. So therefore, he didn't. Okay, let's prove by contradiction. Very often, that proof is used. Okay, let's go on to the next question. So there it is. There is a proof which you can have a look at some time. Now, question 5 says some binomials binomials means the two terms, trinomial 3 terms. So some binomials, such that the difference of two squares can be factorized. Now we know that x squared minus 4y squared is x minus 2y into x plus 2y. But we have been also taught that the sum of two squares cannot be factorized. Right? Like this cannot be factorized. And that is true in that case. But it's not true in general because there are cases where the sum of two squares can be factorized, right? And the example that is given is this one. X to the fourth plus 4y to the fourth. We claim that this can be factorized, right? Although it's the sum of two squares. This is 2y squared all squared. Now prove the statement that it can be factorized by writing it as the difference of two squares. So what I'm going to do is I'm going to complete squares here. This is x squared all squared plus 2y squared all squared, right? Now I'm going to complete squares. So I'm going to put x squared right? So it's you have to add 2 times x squared times 2y squared plus 4y to the fourth. So I've added this thing here. The reason why I added this is now it becomes x squared plus 2y squared all squared. See, when you expand this, you have x to the fourth. The other term, 2y squared all squared, is 4y to the fourth. But there's a middle term, which is 2 times x squared times 2y squared. There it is. Right. But you can't just do this because on the left-hand side, I've got x to the fourth plus 4y to the fourth. You can't just randomly add this object here. You have to subtract it to make the statement true. Right? When you multiply this thing out, you get 4x squared y squared. Now you will see that this is actually equal to the left-hand side. Right? So you put minus 4x squared y squared. If you add this number, you have to subtract it because you must respect the equal sign. But now this is x squared plus 2y squared all squared, and this is 2xy squared. 4x squared y squared is the square of 2xy. But you have a difference of two squares here now. A squared minus b squared is a minus b into a plus b. So that's what we have proved. Prove the statement by writing down this sum as a difference of two squares. What statement? That it can be factorized. So you see on the left-hand side, I've got x to the fourth plus 4y to the fourth. On the right-hand side, I've got a factorization of it. Right? Product of two numbers. So we have proved that it can always be factorized. And then the last part of this is to show that 5 to the power of 4 times 2 to the power of 14 is divisible by 73. No calculators allowed. Right. Now, if so, you might decide you want to do it by hand. You can do that. This is 16,384 plus 625. So you have something like which is almost 17,000. And then you divide that by 73. Show that it's divisible by 73, and you see that you got it goes into it exactly. Right. But obviously I need to use the above result. So I'm going to write this thing down in that form. this is 5 to the power of 4 plus 2 to the power of 14. I want to write this thing as 4y to the 4th. So this is 5 to the 4th. Now let's get rid of the 4 from here. You pull out 2 2's and you're left with 2 to the 12, right? So you're getting it somewhat into this form so I can factorize it. But now I've got 4 and I've got 12 here. I'll have to get both of them to be 4th powers. So you need to write this thing as a 4th power, y to the power of 4. It's 2 to the power of 12 at the moment. So what you have to do is you take 3 2's, which is 8, and multiply it 4 times. 3 2's, which is 8 times 3 2's, times 3 2's, times 3 2's, and you have 12 2's. So that's exactly what I've got here. But now you've got, this is now glaring at us in the face because you've got x to the 4. The 4 is there. And then you've got y to the power of 4. So x is equal to 5 and y is equal to 8. Okay, so that's what I'm trying to factorize. So let's put x to the 4. X is 5. So this is 5 squared plus 2. Y is 8. Minus 2xy. That's 2 times 5 times 8 times something else. Okay, I just want to skip that because I want to first calculate what this thing here is. So you got 25. 5 times 5 is 25. 2 times 8 squared. 8 squared is 64. Times 2 is 128. Right, 8 squared is 64. Okay, we're going to add these two up. 5 plus 8 is 13. 1 plus 4 is 5. So those two add up to this. And then you're going to subtract 2 times 5 times 8. So this part here is 153. And 2 times 5 times 8, 2 times 5 is 10. 10 times 8 is 80. And 153 minus 80 is 73. That's exactly what we needed to show. Right? So you'll see the 73 is one factor, and the other factor is this, that one there, but you have to replace the x's and the y's there also by 7, and you'll get the other factor. So I think you get something like 200. 153 plus 80, which is 253. All right. But we wanted to show that this is divisible by 73, and we have just done that because you got this is equal to 73 times something. We can just neaten it up at the end. Okay. Um, Let me just clear the screen and check to see whether this is how I did it. Okay, I just want to show you what I proved. Oh, there it is. So I'm just exposing this in case you didn't get what I said. And you can factorize. This is factorized, and one of these factors must be equal to 73. I saw that by inspection, I saw that x equals 8, y equals 5. That allows you to prove that 73 is a factor.